All right, I have distributed to you some notes on the area functions. There's a page 1 and a page 2. Page 1 is just generalizations, but we'll mainly be using page 2. So you see this is split up into two parts. On the top, it says for a potential with a decreasing slope, and the bottom we have potential for an increasing slope. And we are, given the matching conditions for the two sides. So what I'll do is I'll just work this out using an example because that's best. So as an example, just suppose, so let's take one side of the potential to be infinite. Okay, so that we have v of x and we have v equal to infinity on the left-hand side for x less than 0. And as a function of x, we have some, potential which goes up like this. And we are given, so we can choose our value for the energy. So we want to find the bound state. So we'll see what bound states are possible. Okay, so this is our problematic point because that's where E is equal to V. And that point, we are going to call BXP. Okay, and that's the structure of the potential. Now what we want to do is we want to find matching solutions for the two sides. So on the right-hand side, I know that I have either these exponentially growing or exponentially dying, types of solutions. So they are either divergent or convergent. So now I want the convergent solutions to the right. So if I am now looking at the, I haven't left much space for myself here, but if I now look at what is happening to this psi of x as a function of x, on the right-hand side, I want a convergent solution. So the convergent solution is something that goes like, e to the minus ib. IB is defined at the top. It's just equals e to the minus 1 over h bar square root of, let me just call it integral p bar dx. So it has that type of solution. So if that is the solution on the right-hand side, because you see I have certain choices. I can choose any one of the choices that I have on the right-hand side. It's a choice among exponentials. So it can be a cosine hyperbolic function or things of that sort. But if I just choose any one of those functions, and in this case I'm going to choose the function which goes to 0 as x becomes larger and larger. So if you look at the integral limits, this is from xb to x, for example. So as x becomes larger and larger, this becomes smaller and smaller. Now, to the left of it, over here, the convergent object is going to be cosine of I small b, which is 1 over h bar, and an integral of, small ib, so it's from x to xb. So you see these limits are always chosen so that they go from some small x to a larger x, so that you always get positive quantities for the integrals. And I have this p of x dx. And I also have a minus pi over 4. So that's it. I don't have to worry about what is happening to the Airy function, how do I match the two functions, etc. If I have e to the minus ib type of function over here, that's what I get over there. Okay? Simple as that. So we have taken this boundary condition. What this does is it assumes this is a straight line here. Okay, puts in the Airy function, matches the two sides to the WKB solutions, and this is what you get. Okay, so these are called connection formulas, and as you can see, it's extremely simple. So we know that on the left-hand side, solutions are going to be like this, right? So normally, if I had a problem like this, seeing that the potential is infinite here, I would start from the left and say that I'm going to use a sine function. But here I am starting from the right-hand side because, okay, that's where my connection formula comes from. So this is my psi of x on the left-hand side. But now I know that this has to go to 0, okay, for x equal to 0, right? When x becomes equal to 0, I want my function, I want my wave function to go to 0. So let me write that out. So psi at 0 is going to be proportional to, there's this 1 over square root of p factor in the front, which, okay, is always there, but we don't need it now. So this is going to be cosine of 1 over h bar integral 0 to xb, okay, of this p of x dx minus pi over 4, okay, is going to be equal to 0. Okay, because that's what psi at 0 is. I have to start my integral from 0. Right? So what is the condition that makes this cosine equal to 0? What does this argument have to be? Okay? Yeah. Okay, so it's going to be pi over 2 plus n pi. So this says 1 over h bar, this integral 0 to xb, p of x dx has to be equal to pi over 4 plus pi over 2 is 3 pi over 4, right? Plus n pi. Okay, let's just apply this to a function that we know. Okay, so let's look at the harmonic oscillator. Okay, so let's apply to v of x equal to 1 over 2 k x squared. So it will be half a harmonic oscillator. Okay. So this is going to be equal to the left-hand side. Let me just look at that piece. Integral 0 to xb of p of x. What is p of x? 2m e minus 1 over 2 k x squared, right? dx. So I have to find out what this is equal to. So this is equal to 0 to xb square root of 2me minus mk x squared dx. Let me pull out an mk. So 0 to xb square root of 2, okay, I took out an mk, so 2e over k minus x squared, right? dx. What's 2e over k? What special point is that? Now applying this to a harmonic oscillator, so it looks something like this. Okay, I gave you a hint. At this point, I have 1 over 2 kb, k times kb squared, okay, k xb squared is equal to e, or kb squared is equal to 2e over k, right? So this is actually our limit. And I'm going to get square root of mk 0 to xb square root of xb squared minus x squared dx. Okay, well, some more algebra. So let's make a transformation. In place of x, let's put something like xb times sine theta is equal to x, right? So dx is going to be xb times cosine theta d theta. So this is going to be square root of mk integral from 0 to, okay, now I have to be careful, 0 to pi over 2, right? In place of x, I'm putting xb, so that will take out an xb from the square root. There's another xb from the dx, so it's going to be xb squared. Okay. 1 minus, let's write it out, 1 minus sine squared theta cosine theta d theta. Well, I don't have any more space. No sense in pushing it, but let's see. Maybe I can put it over here. Okay, so let me just continue with the algebra. Okay, so integral 0 to xb of, let me just write it, 2m e minus 1 over 2 k x squared dx is what we started out with, is going to be equal to square root of mk times x, xb squared, and integral 0 to pi over 2 of cosine squared dx. So what is this integral? Yeah, but you don't have to do that algebra, right? Cosine squared is a nice oscillating function around 1 over 2, right? So cosine squared is something like this. So I'm integrating from here to there, 0 to pi over 2. So So it averages to 1/2, right? Okay, this is clear. 1/2 times pi over 2, so it's pi over 4. Okay, so we are almost there. Where is our equation? Okay, our equation is right there. So it was 1 over h bar 0 to xp p dx is going to be 1 over h bar square root of mk. xb squared is 2e over k. Okay, this is just xb squared. And then I have pi over 4. So it's my integral. It's supposed to be equal to 3 over 4 pi plus n pi. All right, so this is going to be 1 over h bar square root of m over k, and then I have pi over 2 is equal to 3 over 4 plus n times pi. So we cancel the pi's. This thing here is 1 over omega oscillation. So this says, I forgot the E, there's my E. So E over h bar omega c is equal to 2n plus 3 over 2, and I guess that's it. So E is equal to h bar omega c 2n plus 3 over 2. Okay, so we got an energy spectrum. So what are these energies? Well, we have for n equal to 0, 3 over 2 h bar omega c. For n equal to 2, we have 4, for n equal to 1, this is going to be 7 over 2 h bar omega c, and so on, right? Maybe it's better to write it like this for various values of n. For n equal to 0, I have 1 plus 1/2 h bar omega c. For n equal to 1, I have 2 plus 3 plus 1 over 2 h bar omega c, right? For n equal to 2, I have 4 plus 1, 5 plus 1/2 h bar omega c. So what does this spectrum represent from the harmonic oscillator? Yes, okay, so yes, so we have here the, let's not call it n, but something like m equal to 1, m equal to 3, m equal to 5 type of solutions to the harmonic oscillator, right? So if you remember what the solutions look like, this is n equal to 0, okay, or let's call it m equal to 0 for this case. Okay, the lowest energy eigenstate looked something like this. But now I have an infinite wall at x equal to 0, so this is not an allowed solution anymore. Now, if you look at the m equal to 1 solution, okay, that's acceptable because it goes through 0 at x equal to 0. Okay, so this solution is okay. If I look at the m equal to 2 solution, it's going to be something like this. Okay, again, this is out. because at x equal to 0, you cannot have a finite wave function. But I can have, okay, something which looks like, I don't know, which goes through, okay, so m equal to 3 is okay. So I get only half of the energy states corresponding to the harmonic oscillator, okay? So it's amazing that we get, in fact, the exact energy states. So it works quite well for this case. Okay, questions? Yes?
Weren't we doing this for E close to B, but then we extended our analysis to 0 to xb, but then E and B has a larger separation?
What do you mean? Okay, here we are applying this method only at this point, okay, just so that we are okay, sort of preparing ourselves for the other cases when we'll look at both sides. Okay, so here we had the matching condition only here. Okay, so in fact the next example I want to do is where we have, okay, matching at both sides. Okay, any questions? Okay, so let's move on.
Actually, I'm also confused with the same part. We took the integral from 0 to xb, and at 0, E is not close to B. We can apply WKB.
Yes.
Why?
Yes. So near 0, what would we get? Okay. So if I didn't consider this side, if I did not worry about this boundary, I would just look at this piece, and I would say, okay, I'm going to get a solution here, which is going to look like sine, okay, 1 over h bar from 0 to x of this p of x dx, right? So that's what I would write for the left-hand side, because I want this thing to go to 0, okay, at this boundary. And then I would need to match this, okay, at this boundary to whatever I have on the right-hand side. But it turns, in this problem, it turns out to be easier to start over here and then fix the boundary condition over there. So you see, this function is really consistent with that function. Okay, so this is going to give me a 0 over here, which means I will be giving it the proper phase shift so that it goes from cosine to sine at this boundary if I choose my energy accordingly. Okay, so it's really the same thing. Okay, I could have started with this thing here, but then I would need to match it over there, which becomes a little bit more complicated matching. It's easier to do the more complicated matching, okay, so that you get some result, and then apply it to the simpler boundary condition. Okay, but as an exercise, you can start here and go over there and see if you get the same answer. You should. Okay, so let's now look at the case when we have matching on both sides. Okay, so now we have a potential which, okay, this time I have leave some space in the bottom. Okay, so this is our potential, v of x, as a function of x. So it's going to be some general function which goes like that. And now I want to find a WKB solution for some energy E over there. Now you see there are two places where energy becomes, okay, the same as the potential. So I have to do matching here and matching there. Okay. Now, how do I do it? Well, I look at the solutions that I'm going to get in various regions here, okay, where I have something on the right and something on the left. Okay, so the right coordinate I'm going to call xp, the left coordinate I'm going to call xa. So I have to match at xa and I have to match at xp. Okay, so I go to my nice relation of matching conditions. Okay, so here you see the potential is going down. So that is the type of potential that I have at the top. Potential with decreasing slope, okay, at x equal to a. So I want to use one of these equations, one of these forms, and I want to use again the convergent one. Okay? So the convergent one goes like e to the minus ia over here. Okay, the integral is given above, which means that it is going to match something which goes like cosine. Okay, so let me write it out. IA, which is an integral which starts, okay, so 1 over h bar integral starts from xa to x. Okay, so that's how this, the phase of this cosine is defined. P of x dx, and then these phases are important, minus pi over 4. Okay, so that's now matches these two types of functions. If I choose this, my function psi as this, I'm going to get a nice decaying function here. If I give it some other phase, I'm going to get also an, okay, divergent function over here. So that is the structure. It's going to give me a convergent stuff here. Now I have to do the same thing on the right-hand side. So that is now potential with increasing slope. So that's the one in the bottom. And I want a convergent function. So it's going to be e to the minus ib. Okay, I'm not going to even write it down. It's written over here. Now I want the convergent form. So it's going to be cosine. Now it matches everything over here. So it's going to be I small b, so 1 over h bar integral from, where am I, x to xb. So you see these are always from left to right, okay, the integral limits. P of x dx, now minus pi over 4. So that's the type of function that I need in order to match this boundary condition. So this boundary condition says I want this. This boundary condition says I want that. Okay? So in order for this to be a proper solution, that must be equal to that. Okay? So I must have cosine 1 over h bar from x a to x p of x dx minus pi over 4 must be equal to cosine 1 over h bar, okay, integral x to xb p of x dx minus pi over 4. Okay, so these two guys have to be equal. Now, you see this goes from xa to x, this goes from x to xb. So these are not easy to compare. So what I need to do is I need to change this, okay, to an integral which looks like that. Okay, so here I have an integral from x to xb or something, but I need something which has xa to x. Okay, so how can I do that? This is an integral from x to xb. What I can do is I can write a full integral from xa to xb, or the same thing. And then what? And then subtract the interval from x a to x, right? Or the same thing.
xp minus x. xa to xp.
xa to xb, okay, minus, what do I need to do? xa to xp, and, okay, I'm getting tired. X to xp is the last part, so I need to subtract out.
It's correct.
Okay, I think it's okay. All right, so in fact, let's do that. So I'm going to get cosine 1 over h bar xa to x p dx minus pi over 4 is equal to cosine, okay, let's see, 1 over h bar integral x a to xb p of x dx, okay, minus xa to x px dx minus pi over 4. Okay, well, we are almost there, but this one has a minus sign in front. Okay, so this is xa. So that's the integral that I have there. That's the integral, that's the same sort of integral that I have there, but it has a minus sign in front. But what's nice is cosine has this nice symmetric property, so I can just multiply this by minus 1. So this is going to be, there's 1 over h bar here. So this is going to be cosine 1 over h bar xa to x p dx, okay, minus 1 over h bar xa to xb p dx plus pi over 4. Now, okay, we have here some arguments. We have some other argument there. So let's make it really identical. So cosine 1 over h bar xa to x p dx, okay, minus pi over 4. Okay, so this is exactly what I have over there. But now, of course, since I put a minus pi over 4 here, I have to put a plus pi over 4 there. So let me write it like this: 1 over h bar x a to xb p dx plus pi over 2. Right? So that together they make pi over 4. All right, so this says now cosine of something is equal to cosine of the same thing plus something. Okay, actually I have one more freedom. I started with some function from the left. I can always multiply these things by plus or minus 1. So this is really plus or minus cosine, and this is plus or minus. Okay, so there's, this thing doesn't have to be equal to that. It can also be equal to minus that. So if I have two cosine functions like that, okay, what should be the difference here so that they are equal.
And pi.
Hmm?
And pi.
And pi. Okay, so if I have something like cosine x is equal to plus or minus cosine x plus this question mark, that question mark can be n times pi. Okay, so if whatever remains here is equal to n times pi, I am okay. So let's do that. Actually, I need this result again because if I'm going to, so let me just erase this partially. All right, so where are we? So this says if this thing is to be equal to that with a possibility of a plus or minus, okay, degree of freedom, then this says that this object here, 1 over h bar minus integral xa to xb of p dx plus pi over 2 is equal to n pi. Okay, or I can say xa to xb p dx is equal to, there's an h bar, there's also a minus sign, and I have n, let's see, 1/2 minus n, right? Did I do it correctly? No. Minus n, okay, p is equal to plus, okay, so it's going to be like this. Okay, but this is going to be a positive value, okay? So I can add n pi or subtract n pi, so I really need to add this thing because I'm going to need to get a positive result here, okay? So I can, okay, it's just saying that I can add plus or minus n here. Okay, so I have that. What does that mean? That means I have to now do my integral from xa to xb of this quantity 2me minus v of x, that's our p of x, dx has to be equal to n plus a half, where am I, h bar pi. All right, so if now I choose, so this is for a general potential. If this v of x is equal to 1 over 2 kx squared, then it becomes the harmonic oscillator. And then you see I have this equation. This left-hand side becomes an integral from xa to xb of square root of 2me minus 1/2 kx squared dx. But I did that calculation over here, except that my calculation was only for half from 0 to xb, but it's a symmetric integral, so it's just going to be twice what I obtained earlier. And where is that? Okay, so that is going to be right here. Okay, so that is going to be equal to 1 then 1 over h bar, so I do my stuff correctly. 1 over h bar times that is equal to 1 over h bar, okay, square root of m over k times pi over 2. Okay, so we did that integral earlier and obtained this result. So this is now going to be equal to n plus a half times pi, because I divided by h bar. Okay, so let's just cancel these 2's. So I also have an e someplace, right? So this gives me e is equal to, this is 1 over omega c. E is equal to, who's going away, h bar omega c n plus a half times, no, the pi's cancel, right? And that's it. So you see, I can get the exact energy states from the from that. Okay, so what next? There are a number of things that you can attempt, which are given as problems in your textbook. Let me just identify some of them. You can look at the general tunneling problem. Okay, so so this is a case where, again, you have some v of x, which is 0 here, but then sort of increases, and then it's 0 again. So as a function of x, you have something like this, and you choose an energy, and now you have that. Now you have, again, 2 turning points, xa and xb. You know the solutions all the way to the left, e to the minus I kx, a times e to the minus kx, b times e to the plus, no, a times plus a minus I kx. You see, these are already in the form of WKB solutions. Okay, they are exact, but this is what WKB would give us anyway, right? Because potential is constant here. So K is just h bar. K is just going to be equal to 2me minus v. Okay, so if v is constant, that's your momentum. It's equal to h bar k, and you know what these things are. So the solution on the right is also e to the I kx type of solution. So those are WKB solutions. They will start to change when the potential starts to increase. Okay? So you are going to get here solutions which look like, so let's look at what's happening on the increasing side, what the notation says. Okay, so this is going to give us the 2 types of solutions which correspond to, okay, e to the plus or minus IB type of solutions. Okay, IB is over there. And then I times IB. Over here, it's going to be e to the plus or minus, you are going to get just e to the plus IB, I times IB solution. But in between here, in the middle, okay, we are going to get these exponential type of solutions, in fact, we are going to get e to the IB and e to the minus IB type of solutions, each with their proper coefficients. And you'll have to match this to that, that to that, etc. Okay? And in principle, you can just work this out. Again, the problem is with, if you look at all these IBs, small b's and capital B's, you have integrals which look like p of x dx, where p of x is defined by this function. So it depends on whether you can do the integrals or not. Okay, so the problem is doable or not doable, depending on the difficulty of the integral. Okay, so this is the general tunneling problem, but there's also another interesting problem in your textbook, which is the problem of the double well. Okay, so you can look at the possible solutions when you have four turning points. Okay, so obviously things get more complicated then. Okay, but you see this is a nice and powerful method which you can use, quite accurate. You have to be able to do the integrals, and if you can do the integrals, you get quite accurate results for the wave function and the energy. Okay, I'll stop here. So we'll meet again on Friday.
Why do we